Okay, let's talk about fiber optics, right? Anybody got any questions so far about the makeup of a typical 900 micron cable? This is a core. We're doing 62.5, 125 cladding. We got a 250 micron buffer coating and a 900 micron type buffer. All that makes sense? Everybody okay? Any questions on that? Of course, we can't see the core. Even though we know the core size, we can't see the core because the cladding in the core is one unit. Everybody understand that? And of course, we can see the coating. This gives the cable a gray type or translucent type coating. And then the buffer coating, I told y'all, is either going to be tight buffered or loose buffered. We use loose buffered for outside and underground use, and we use tight buffered for inside use. So all our cable is tight buffered cable. The light frequencies, these are the standard light frequencies used for fiber optics. We're going to be using multi-mode cable, which is 850 microns, or nanometers, excuse me. But when we test this, we're going to use a light meter, and this is one of the first things we'll use. And I'll have to look at these. These are brand new. We got another set, but these have never been used before. A light, and of course, what we have to do is we have to have a source for light, right? Everybody okay there? And what we have on this one is we have two wavelengths, and I don't remember. I'm going to have to look it up and see the wavelengths are. This is 850 nanometers and 1300 nanometers, which should work for anything if I can get it to turn off. But here goes. So this is a source right here for light when we check the meters out or check the cables out. And we got two wavelength meters, and then this right here is going to measure the loss of the cable, and we're going to try to get around to this today. Dang it. So we talked about state of light, nanometers, went through some problems, talked about total internal reflection. Are you okay? And what's refraction? When light refracts, that's when the light changes direction when it passes through two media that has different coefficients of reflection or refraction. Critical angle, as long as we stay below the critical angle, then it's going to bounce down, right? If we get above the critical angle, then it's going to refract. Talked about index of refraction, numerical aperture. Talked about attenuation, which is pretty much the same in conductors as it is, metal conductors as it is in fiber conductors. Talked about scattering, talked about core offsets and different problems that we have that we're not in control of. So we're not in control of core offset. We're not concerned with non-circularity. What we're concerned with, of course, is how we terminate it, right? Talked about critical rays and actual rays. Y'all understand that? Are you okay there? Talked about model dispersion. We've talked about a mode. What's a mode? Oh, it's written right there. So we're going to deal with multi-mode cable or fiber. What does that mean? Nobody know what's a mode? I mean, if you can, hopefully you can read. What's a mode? So I have two categories of fiber cable. We have what we call multi-mode and single mode. So what does multi-mode mean? It means it's got more than one path, right? You understand? What does single mode mean? There's only one path. You all understand that? We have two types of multi-mode cable. We have what we call stepped index and graded index. So we're going to be dealing with graded index cable or fiber. What does that mean? So what's the difference between stepped indexed and graded index? And what does the advantage of each one of them hold? I'm going to sit here until we come up with these answers. I mean, we're not going to move on. I mean, I don't know what's going on, guys. This is the weirdest semester I've ever taught since I've been here, since 1982. Where people don't show up for class on time, or they just sit here like lumps on a log, you know. So what advantage? What's the difference between stepped? All plastic is stepped indexed. Glass can either be stepped indexed or graded indexed. So what's the difference between these two? If we don't understand this, then we don't know fiber at all. I mean, these are basic things about fiber. Mode is a multi-mode. You need to know what that means. Single mode, you need to know what that means. So stepped did what? Well, step means the paths are not controlled. So these lights they're bouncing down through the cable and they're moving between the critical rays and the actual rays. So they're going all different types of paths. Here, if we have light that varies in color, then we're going to have to worry about chromatic dispersion, right? Because once it bounces off the side, they're going to definitely so shorter wavelengths are going to do what? They're going to bounce off closer together. Longer wavelengths are going to bounce off further apart, which means the lights are going to arrive at our receiver at different times, which means the pulse is going to be spread out, right? You understand that? So what advantage does step index have? I mean, why even use it if there's no advantage? Ultimately, everything, even when I go out and buy a car, I'm not a Johnny Depp or something like that. When I go out and buy a car, what's one of the main things I'm looking for? Or when I go out and buy a house, when I go out and buy anything, when I buy anything, one of the main things I'm looking for, guys, is what? I mean, I'm not a millionaire, right? You understand? What's one of the main things I look, huh? I look for price. So I'm trying to get a vehicle that does what I need to do, right? You understand? Have the options that I want, and sometimes I give them up, right? Understand? For a price I can afford. My wife wants to know what's the monthly payment's going to be. That's all she cares about. She don't care about the cost. She knows how much we can pay every month for something, and that's what she's looking for. So I have two types. I have graded index, I have stepped index, and then I have single mode fiber. So which one will be cheaper, stepped index or graded index? Step's going to be a lot cheaper. So that means if I'm going to run something 100 feet, I might look at this. If I'm going to run something 10,000 feet, then stepped index is just not going to make it because the pulses would disperse along the line, right? You understand that? So real cheap stuff. So all the fiber that we have over there on the manufacturing line are stepped index. Because why? The lengths that they have to run, or the distance they have to run, is so short. Graded index, what they do is we control the path that the light follows, and we reduce the time between the critical rays and the actual rays, which means a graded mode index, graded index multi-mode cable can run at higher speeds. It can handle offset colors a little bit better, but the problem is what? Between stepped index. It what? It costs more, right? You understand? It costs more. In fact, graded index cable is basically the most expensive cable we can buy. And then we have single mode cable. Single mode cable is cheaper, but single mode cables has to run with light at one wavelength. So single mode cable is going to use laser devices, right? You understand that? Which means the end of electronics is more expensive. So even though single mode cable costs less money, the entire system costs more than a multi-mode system. Y'all understand that? So which one are you going to use? Well, which one you're going to use depends on how far and how fast you need to send the data. And what you're going to do, if you understand this, is you're going to go out there and you're going to buy the cheapest cable you can buy to do what the installation that you need to do, right? Does that make sense? Everybody understand that? I mean, if you don't understand cost over use, you'll never make it in here. I think I told you about my neighbor. He had his electrician's license. He never worked on his own. And they bid on a house, and he lost like $10,000 on that house. And why? Because he didn't understand things. I could run 12 gauge cables. I could run 12 gauge wire through my whole house. But now my cost is going to be a lot more expensive because the plugs are more expensive, the wire's more expensive. When odds are I don't need that type of amperage for standard wall outlets, right? You understand? Now here we run 12 gauge wire and use 20 amp receptacles, because this is not a house, this is a commercial application, right? You understand? And you can look on the wall right over here, you can see this is a different plug than what you have at your house. Because this is a plug for a 20 amp device, and your house plugs are 15 amp supplies. Go down to Lowe's and look at the price of these things and compare them to the price of a 15 amp plug. You can get 15 amp plugs for almost nothing. I mean, less than, I think they're about 80 cents a piece. So multi-mode, so we're using graded index fiber optic cable. But the splicing technique is basically the same for all these, and termination. So this is graded index, which is what we have. And it shows you, this is a nice picture right here. I don't forget that. We went over the different single mode. The core is so small, it only allows one path to go. So we're looking around 9 microns on this thing, which is 1/6 the size of a 62.5 micron core, which is what we're dealing with. And that was the end of this lecture. So we just went back and reviewed. So y'all got any questions on that? Yes or no? Huh? That's a good question. I'll go back and look. We got quite a few. Uh, some we're going to do it as a class. In fact, the first one we're going to do today is as a class. And what we're going to do is we're going to learn how to use these meters, and we're going to check we're going to use this to measure some real long fiber optic cables, and we'll do that as a class. Since Chase is not going to be here, he's got an interview with Mercedes today to get into their program down there. We're trying to get into it. I think he'll succeed. I think he'll be okay. So what we're going to do now is talk about the different types of cables, the different types of connectors, the different types of splices. As soon as it finishes loading. No, this is not what I want. Basically, the pulling devices that we use for fiber cable is basically the same as we use for copper. So we use fish tapes, we use clean grips or wire mesh grips, and this is what I showed y'all that. But we never pull with the fiber conductor. We always pull with the outside jacket and mainly the Kevlar. So we have a power puller, which we looked at before. There is a little different with fiber in that we never, when we lay this stuff out to be pulled, you notice what they show here is they usually lay it on the ground in a big figure eight. Because we don't want this to get cramped, we go ahead and pull it off the reels and lay it out like that. Fiber movement in a loose tube. I didn't see that. Let me. I'm supposed to have some loose tube in here. I don't. For some reason, the fiber is sticking out of this one, but it's still got the coating. So this is loose tube fiber right here. Well, this is the type of fiber we usually run through the ground or outside. Through the ground is very, very important because y'all know the ground moves. It's been a long time since we've had rain here. And the curb out in front of my house on the circle, I've noticed that the ground is actually separated from the concrete curb. And we get cracks in Alabama in this time of year because this is our least. This is when we usually get least. It vibrates, you know. If you're about trying to crack, your ground always vibrates, you know. So this is why we don't use what we call a tight buffered cable outside or in the ground. So loose buffered, what we have, of course, is the outside buffer. The inside buffer is not in contact with the coating. So what this does is it gives the fiber, so all the outside components can do was they can move around, and the fiber basically doesn't move. And we call this. We've already looked at cutting it with a jacket stripper. Of course, we have what we call a 3-hole stripper for fiber optic cable. Now, of course, the loose buffer that we showed you, we would have to strip that differently on the outside jacket on that. Let me find these. So we have different techniques. Normally what we can do, of course, the outside buffer, you can strip this with just any standard stripping tool. Everybody understand that? But all we do is we basically use it to cleave or cut into or prescribe the outside jacket, and then we pull it off. So we don't pull it off with a stripping tool, right? Because we don't want to damage the Kevlar or put any stress on the inside conductor. This is another form of stripping tool. We have some of these. These are made for specific size jackets and coatings. And y'all can see the little groove. I can go get one of these and show it to you. All right. And it's on YouTube. I'll put a link on there. One thing that you need to understand is this thing right here called bandwidth product and the dispersion rate. These are different ways that we rate a cable, and we can understand on the next slide the actual difference between the speed of this. So distance bandwidth product, this is for multi-mode, we do it in megahertz per kilometer. So this is the way the cables are rated. In single mode, it's in picoseconds per nanometer per kilometer. So this would give us an idea of how fast this cable right here can actually operate, and we'll look at some actual ratings. So multi-mode stepped index plastic. We run this at a bandwidth of 660 nanometers, which would be visible, right? You understand? You can see this light. It has 5 megahertz per kilometer. Now, what does that mean? Well, that means if I run this cable a kilometer, then this cable would be okay. What if I needed to run it for 2 kilometers? Well, I couldn't get 5 megahertz, but I could get 2.5. Does that make sense? So what the megahertz per kilometer tells you, so if I go to 2, then the ratio is going to stay the same. You understand what I'm saying? Yes or no? So that means this has a ratio of 5 to 1. So that means if I double the kilometers, then my speed is going to half. If I half the kilometers, so let's say I do it 500 meters, then that means I could run the cable at 10 megahertz. Y'all understand this? That makes sense? Yes or no? Everybody okay? You okay, James? Where are you going? Okay, what we're using is, then we have stepped index glass, which you run at 850 nanometers, which we can still see this. This is a red, dark red color. This has a bandwidth product of 20 megahertz per kilometer. So what does that mean? Well, that means if I ran it 2 kilometers, then the best we should do would be 10 megahertz. If I run it 500 meters, then we could reliably run it at 40 megahertz. We're using graded index glass, 850 nanometers. So our cable's rated at 600 megahertz per kilometer, which is pretty good, right? You understand that? So, but if I ran it 2 kilometers, then we would have to drop it down to 300 megahertz. Everybody understand that? That makes sense? Multi-mode graded index running at 330. This cable is designed for this light. This goes me from 1 gigahertz all the way up to 2.5 gigahertz per kilometer. Now, single mode glass, which we have some over, I need to go over and get it, 310. Of course, you can't tell the difference. Y'all understand that, between single mode and multi-mode, because what they do is all these right here run a 125 micron cladding. So that means if you got a micrometer out and you measured this glass, the single mode cable would measure exactly the same as the multi-mode cable. So what they do is they came up with industry standards on how they do that outside jacket. So what they've done is they have color codes for the different jackets that we have, and that's about the only way you can identify single mode from multi-mode. Single mode cable is anywhere between 700 and 76,800 to 300,000 megabits per kilometer. So we got two options. We can reduce the distance and increase the speed, or we can reduce the speed and increase the distance. Does that make sense? Are we okay? All glass fiber runs a glass core and a glass cladding. That's what we use. So this is used by a lot of single mode fibers, which is used by the telephone company, closed CATV, and network backbones. A network backbone is the connections or the conductors that carries everybody. That makes sense. And then what we do on most networks is we take off our backbone, and so we got one fiber that feeds this building over to building A. And then that, of course, would be the backbone for this building. Does that make sense? And then when we get into this building, what do? We split it up all over the place. So your backbone needs to be what you got, your high-speed cable, and then on the inside, you need to run it depending on how far you're going to go. So if we look at the switch up at the top up there, we see the orange cable coming in. That's the fiber that goes over to building A. And then you see all those other ones that's hardwired. You see the network cable up there. That's rated at 100 megabits. So that single mode fiber, it's running a lot less than a kilometer. It's just going up to building A up there. Multi-mode, we use this for the local area networks. We use this for backbones within a building. We use it for video transmission, process control, which is what our lines are using over there, right? You understand that? And of course for security systems. No, that's multi-mode. We don't need that speed. I mean, good gracious, so it would cost a lot more. So this is per kilometer. How far is it up to building A up there? That's not even a kilometer. It might be 500 meters. So if I install this, it would cost me a ton of money, right? You understand that? But we don't need that speed. In fact, we don't need the fastest networks we got here are 1 gigabit, which would be in the range. So we're using this guy right here, 850, 600 megahertz. The fastest we have over here, I believe, is the 100 megahertz network. So what advantage does multi-mode have over single mode? Why didn't they use single mode? Well, the system's cheaper. The cable actually costs more, so single mode cable is cheaper than multi-mode because they got to put all those layers inside that glass tube. So when you saw that glass tube on the outside, that is the cladding. That's what ends on the inside. And then what they do is they coat the surfaces with different materials to get different cores. And so on multi-mode cable, on graded index, they have to put more than one coating on the inside of that tube before they shrink it down. So multi-mode graded index is more expensive, but it uses standard electronics. It runs at 850 nanometers, which means we can use light emitting diodes instead of laser diodes, which means the system is going to be what? Cheaper. The cable is more expensive, but the entire system, and that's what you're looking at. Single mode cable actually costs less. We could look it up on fiber instrument sales, and we could see the single mode cable is cheaper, but the electronics that run the system cost a lot more. So if we use this, then the whole installation system would be a lot bigger, right? You'll understand. That's like the F4 Phantom. It ran 2 big old jet engines, and the airframes could not handle the speed that those engines could push the plane. So what they never ran those engines at 100%. because the airframe couldn't handle that. Now, what they did it for, it was for backup. So if they lost one of their engines, they could still really push the plane, right? You understand that? That plane could fly in excess of Mach 2, which is twice the speed of sound, but the engines couldn't, the airframe couldn't handle the engines. So what we're saying is I'd spend all this money on all this information, right? You understand? But we never used the bandwidth. So that's one thing you need to understand if you're in on these systems and why they chose these different things. Of course, it all boils down to what? One thing. Just about everything boils down to one thing, and what's that one thing it boils down to? Cost. You know, the cost of the system, the entire system, not just the cable, but the cost of the entire system. So hard-clad silica, that's what we use. Multi-mode stepped-in. I'm sorry. This has a lot. All glass, that's what we're using. It's using hard-clad silica fiber. It has a glass stepped index core, and it has a hard plastic clad. So this is going to be cheaper, but it's going to have a lower bandwidth product, right? You understand that? We have plastic clad silica, multi-mode stepped index core, soft silicon rubber clad. And so these are just different advantages of the different type of cables you're going to buy. And of course, what does it do? Well, we're trying to end up with the cheapest fiber we can get to run the system we need to run. And that same thing true if you're an electrician. What are you trying to do? You're trying to make the cheapest system you can that still does this, that performs the specifications of what we need to do. Plastic optical fiber, multi-mode step index core, plastic cladding usually operates at a visible wavelength of 660 nanometers. Of course, the advantages of plastic is its cost, it's rugged, it has a large core, very, very simple splicing. You can cleave this or cut it with just an X-Acto knife. Then you sand it down to get that perpendicular surface. Real easy to work with. The end electronics is very cheap. So I'll show y'all some standard end electronics for plastic here in a minute. Tight buffer tube, this is what we're using. Tight buffer tube or jacket, the inside diameter of the buffer is equal to the outside diameter of the fiber conductor. Now remember, the fiber conductor consists of three things. What does the fiber conductor consist of? The actual conductor itself. Oops. Did it again, guys. I need to remember what slide I'm on. So what does the conductor itself consist of? So the conductor consists of the what? Core, the cladding, and then the buffer coating. That's the conductor itself. Then we put an outside buffer on it. The outside buffer may or may not be, it's not the outside buffer. The actual conductor buffer is actually, we got two types. We got what we call a tight tube or tight buffer, and then we have what we call a loose tube or a loose buffer. A tight buffer, the buffer is in contact with the coating, with the buffer coating. Loose tubed or loose buffered, the buffer is not in contact with the buffer coating. So probably what I need to do is change the size to say, saying conductor to make that clear, is change that to say the buffer coating, right? Would that make it more clear? So where does these slides start at right here? So that makes sense now? Makes sense? Are you okay? The outside diameter of this is usually 900 microns. This is what we've got. The buffer is in direct contact with and that's on there twice. That second time don't need to be there. Now, the advantages of this is we usually use this in inside cables. Of course, the purpose of the buffers altogether, even the buffer coating and the buffer jacket, are what? Add strength to the fiber, makes it easier to terminate, and of course, it holds the buffer coating. And it holds broken fibers together. That makes sense? So this is a basic type buffer cable. This is what we have. Multi-mode, it's going to have an orange outside jacket, which they call the sheath. It's going to have what? It's going to have a Kevlar. It's got a buffer tube, buffer coating, or inside buffer, and then we have the fiber itself. So we have the glass fiber, and then we have the fiber coating, also called the buffer coating. Then we have a what? Then we have a buffer tube or inside jacket. Then we have the aramid, which is the Kevlar, and then we have the outside buffer, or the tight buffer. Let me get these terms straight myself. Okay, so this is what our cables are made of. Are you okay? Of course, what's nice about having these buffers is that you can have a break inside the cable and you'll still get some light through the thing. Now, it's probably going to attenuate a lot because we're going to have that reflection coming off that break, because that break is probably not going to be perpendicular, but at least the cable might operate. And this is one big advantage of having a tight buffer tube. Loose buffer. The inside diameter of the buffer is much larger than the outside diameter of the conductor. The length of the fiber can be longer than the length of the tube. The tube can contain more than one fiber conductor. The tube is usually filled with water blocking material, and this gives us what? Mechanical isolation and resistance to moisture. That makes sense? Are you okay? So this would be loose tube. This is what we passed around, right? You understand that? And what the advantage of loose tube, this is usually going to be our outside cables, the ones that's running through the ground, the ones that are running up on power poles. This is probably going to be loose tube. This is probably going to be a loose tube fiber. So now the outside can do what? It can vibrate and the fiber itself won't move. So it has what they call a loose tube dead zone. It's where the fiber's going to be. Other cable parts: strength member, outside jacket, inner jacket, gel fill and water blocking compound, binding tapes and yarns, armors, ribbons, fillers, loose tube, single fiber per tube, loose tube, multi-fiber per tube, central buffer tube. We're going to look at ribbon fiber, star and slotted core, and premise and breakout cables. This is the kind of stuff we're looking for in a cable. So these are some of the terms we should look for. These are the designators on the jacket. I'll see if I can find a piece of jacket that's got all these designators on there. So this is OFNR. Of course, we need to. These are all tangled up. Black Box Corporation. So this is the information that we're going to find printed on the outside jacket. As soon as I get one of them untangled. might just pass it around. So let's see if this has got it on there. And we'll see if this shows up. If it won't, it's on the outside buffer. We're going to have a lot of information that tells us about this fiber. This put out a company called Chromatic Technologies Incorporated, 500 series 5125. So what is the 50? What would y'all think? Sort of, but we don't say wire gauge, right? So 50 is the size of the core. 125 is the size of the what? The cladding. That makes sense. Arco 510 type, this is OFNR. Fiber, this outside jacket is OFNR. It's not focusing on that. I'm trying to get the camera to focus in on my too. That's one thing about auto-focusing things. That and that one will give you the ability to. So here goes. So this is the outside is OFNR. So OFNR. So what can we use of this? Stands for optical fiber non-conductive riser. OFNR cables are used in riser areas, which are building. So when we talk about a riser cable, that means this cable has the ability to run vertically. If it's not a riser cable, it means that cable can only run horizontally, right? Does that make sense? Okay. So that means this is a riser cable. So we can use this vertical shafts that runs from one floor to the other. OFNR cable cannot be installed in the plenum area. Y'all know what the plenum area is. What's the plenum area? Yeah, this is the space between the what? Between the suspended ceiling and the actual ceiling of the building. It gets extremely hot up there, so that means we cannot run this cable through the plenum. It's not plenum rated. Does that make sense? So if it had an OFC or if it had an OFCP rating, then what is this cable right here? What does the P stand for? This is plenum cable, so we could do what? We could run this in the plenum of the building. And a lot of commercial buildings has a plenum. Now originally a plenum was used for a return for the air conditioner. The air conditioner actually used those. So if you go into my office, you'll probably see a vent up there. So, or it's where the air conditioner ductwork runs. So this is not in this building. This is I'm sorry, it is. Can y'all see that big old vent over there on the side over there? So that means this is a true plenum. But over time, what it's become is it's actually a space between the what? Between the between a suspended ceiling and a real ceiling. So this building does run a plenum. So y'all can see the return for the air conditioner up in the corner over there on the actual ceiling. So these are the different things that we could run. So OFCG, this is optical fiber general purpose. Then we have different cables that have different fire characteristics. We have riser cable, we have plenum cable. This is loose tube single fiber. This is basically what I passed around to you. So what we have is we have several loose tubes, and each tube only has what? One fiber running through it. This makes sense? So these are some pictures right here, and these are basically what I had. Now usually the loose tube, single fiber loose tube, is going to have a gel inside that loose tube. And it is sticky stuff. Y'all didn't get that on your hands, did you? It won't hurt you. Then we have loose tube multi-fiber, where they use one loose tube and then they use several fiber conductors inside the same tube. Loose tube multi-fiber. Then we have what we call a central buffer. What we have is we have the fiber, we have a buffer tube around each fiber, and then we have a strength member coming out on the outside. So this would be an example of central buffer. Okay. Ribbon, this is what the telephone company really likes to use. We don't have any ribbon fiber, but we do have some ribbon. We do have some standard ribbon cable in here somewhere. It looks basically the same. So we call the sub cable ribbon cable. These were used inside computers for years. This is not fiber. This is copper. Can you see? I got the name ribbon cable, which is pretty neat. So this would be an example of a ribbon cable. All these buffers right here are actually connected together. So this is what the phone company uses a lot, because that way you're not dealing with multiple fibers or single conductors. And they have special fusion splicers that splices these ribbon cables together, by the way. It's really neat. A star slotted cord. And this would be a star. It's got an actual armor outside on it. This would be really neat for outside type situations. Premise cable. Now we have some of this, but it's in a spool over there. Ours is what we call a multi-breakout. So we have a premise cable. This is divided to be run inside the premises, or this is also cable that runs inside. And what we have is we have a single fiber, and then we have the buffer tube. Then we have a central strength member, which is usually a fiberglass rod or a metal rod running down here, a flexible strength member, and then we have the outer jacket. This is what we have over there. This was donated to us. We got probably around, I don't know, maybe 10, 15 meters worth of this stuff. And what we have is we have inside this inner jacket, we have multiple fibers running in there. We run these. It's called a breakout cable. So this might run into the building, and then you'd strip off the outside jacket, and then you would run these. Then you would run these, and then you'd strip off the outside jacket, and then you'd break these out. Right? Does that make sense? We have some of this, like I said, but it's in a big old row. So, taped together over in Building A, and I just couldn't carry it to bring it over and show it to you. We have a pretty good deal of that gel-filled loose fiber over there too, but I can bring that over. So this is the maximum recommended installation load. Maximum load can be applied during installation usually between 150 pounds to 600 pounds. Minimum recommended long-term bend radius is, for rule of thumb for fiber, is 10 times the diameter of the cable. Y'all understand that? I think that's actually on the... Now, if you have the information on the cable, you're supposed to look it up. If you don't have the information on the cable, rule of thumb is your bend radius is 10 times the diameter of the cable itself. Does that make sense? Everybody okay? So what you do is you measure the diameter of the cable, and then that would give you the max or the minimum bend radius. Minimum short-term bend radius is 20 times the diameter of the cable. So if you are pulling it, this would be a short-term bend. Then we could look at 20 times the diameter of the cable. Long-term bends, we could go back down to 10. Everybody understand that? That makes sense. Any questions there? We have three types of connection systems. We'll get through this and we'll try to look at some plan. Precise alignment required to achieve efficient transfer of fiber retention. We need to make sure that our connectors prevent fiber from moving toward or away from one another, and in protection, unnecessary damage to the fiber end. So this is our connection system has to provide all this. These are the three main things they have to provide. So when you look at that fiber that I passed around, you were looked at, there was connectors on those ends. So not only are we talking about, when we talk about a connection system, we're talking about splices and we're talking about terminals. Everybody understand that? Are we okay? So these are the main causes of signal strength in connection. Radial offset, misalignment, which we've already seen, lateral separation. These are the pictures. Radial offset, misalignment, lateral separation, or lateral misalignment, angular mismatch, or angular misalignment, numerical aperture. So I use the wrong cables. So I come in with a single mode cable on this side, and I come out with a multi-mode cable on the other side. That's going to give us problems. These are what we control right here. These last three. What's those? Lack of cleanliness, lack of a smooth surface, and then, of course, surface or Fresnel reflection, because this would be how accurately we cut that thing. So when we cut that in fiber, by the way, we call it cleaving. We'll look at that in a minute. We're looking for a perpendicular surface. So offset radial alignment. So if my connectors do this, y'all understand that that's not good, is it? Lateral separation or misalignment. So that means we don't have the two fibers doing what? They don't come in contact with each other. Or the light. Angular mismatch. So one comes in this way, one comes in that way. Numerical aperture mismatch. Core diameter mismatch. So we're using diameters. So this core that I passed around, it's got a blue surface, it's got an orange coating on it. But it's 5125. The cable we're using is 62.5 125. But they both have orange outside jackets, right? You understand that? So the cables themselves look the same. The cladding is 125. Our cladding is 125. But if I did our 62.5, which would be this guy on this side, and over here we had what? We had 5125, 82.5, 125. They look exactly the same because the cladding is 125 on 125 microns on both of them. Y'all understand the problem? So what would happen, odds are this guy would be okay coming this direction, but if light was going that way, we would get a what? We would get a lot of attenuation. Lack of cleanliness. So you don't clean this stuff right when you splice it together and we get something in there. Lack of a smooth surface. So notice here, the surface, it has cracks and stuff in it. And then surface Fresnel reflection would mean we don't get them close enough, we don't have a space in here, and when it hits this side, it does what? It reflects back. 8 causes of signal loss in a connection. Average loss in pick your micron. This is average loss. So our average loss for the cable would be what? Average would be, now this is in dB. So this would be the average loss of the cable. Standard deviation, and I have to go back and look at that, guys. So these are what you're in control of, right? This is what you're in control of. Cleanliness, an unsmooth surface, and lateral separation. Y'all understand those? Everybody okay there? We have 2 types of splices. We have what we call permanent. We have semi-permanent. We have mid-span splices. We'll look at pigtail at termination end. The splices that we have what we call a fusion splicing. So we have a fusion splicer here. Ours is a single-strand fusion splicer. And what we do with a fusion splicer is we literally melt the glass together. This should be the most accurate splice or the best splice you could make. Our fusion splicer is a single splice fusion splicer, and cost us almost $8,000. So this is the fusion splicer. Please don't drop it. And this is not one of the most expensive ones. This is single strand. When you get into some of those, it actually does fusion splicing. Here you go. This is the actual splicer itself. This guy here is portable. It's really neat. We plug ours in. We don't use the battery. So these are for fusion splices. We have mechanical splices. We have 2 types. We have one called a fiber lock, and we have one called an ultra splice. The ultra splice is a semi-permanent splice. So this is an ultra splice. I'll pass this around. I'll take this out right now. This is a semi-permanent splice, which means we can remove the splice without recutting the fiber. A mechanical splice, a permanent fiber splice, like the fiber lock, if something happens to the splice, you got to cut it out of the fiber. We like this one. We have what I like about this one is that you can actually see the inside fiber. It's real hard, but you can tell. We're going to show y'all. We have a light source we can put on the fiber, and you can actually see using the light source. You can actually see when the fiber makes connection. So that's what we would call a semi-permanent slice. I couldn't see the. So the fusion splicer makes a permanent splice. Fusion splicers are really, really neat. Originally, it took us a long time to get the money in place or get a grant where we could buy that thing. But we had the guy from Pimco Mines down in Adger. By the way, your charger does no good if you don't plug it in. That was my computer telling me that. So we'll let y'all. We have the FiberLock splices. I didn't see one in there right off the bat. These are permanent splices, and then the semi-permanent, which would be the ultra splice that we just passed around. So a fusion splicer, what a fusion splicer does, it usually melts everything together. So once you've got a good fusion splice, you can't even hardly see it. A mechanical splice, we're going to have some type of alignment sleeve that we're going to put that. Normally what we have in a mechanical splice is we have what they call an optical gel inside there. And it's a really, really clear gel. It has really good properties. And that way, if the two fibers don't exactly touch, we still get a pretty good splice. Now, the advantage of fusion splicing is you pay a lot of money for your splicer. It makes extremely good splices, but it would be your cost per splice. So if you're going to do 1,000 splices, these guys cost about $8-9 a piece. That'd be $8,000, right? You understand? And you're doing 1,000 splices, then you'd buy a fusion splicer, because a fusion splicer is going to give you a really good splice. Once you learn how to do them, they give you a really good splice every time. So we'll probably do a fusion splice as a class, and then we'll let y'all do a mechanical splice. But if I only had to do 1 or 2 splices, I'm not going to go out and buy an $8,000 fusion splicer to do 1 or 2 splices, right? Does that make sense? So here it depends on. So really, we don't need a fusion splicer with the number of splices we made, but we need to let you see how these things work. So that's why we got it. So here's our fusion splicer. And these are your ultra splices. This is what we passed around. This is FiberLock. So FiberLock, you put this in a little special thing. You push your fiber in there. You strip it to precise lengths. You put the fiber in there, and then you push them in until you see a little hump. It's got the procedure on the actual splicer itself. And then when you crimp this thing down right here, that sucker's permanent, right? Does that make sense? And if you needed to remove a permanent splice, you're going to have to cut it out. If it's a semi-permanent splice, you can just unlock it and pull it out. This is a Corning splice. We also have these. I can't find the little unit. These are what we call splicing trays. So your splices are going to go into a tray. And what the tray is in there, it's going to replace all the mechanics that are in there by support. This is a typical splicing tray. So when you have to strip all that stuff off to splice this cable, you're getting rid of the Kevlar, you're getting rid of the outside jacket or the outside tube, you're getting rid of the tight tube, you're getting rid of the coating, everything, all the protection for the glass, for the fiber is gone. So you got to strip off every bit of that stuff to splice it, right? You understand? So what we do is we put this inside a splicing tray, we bring it in, we loop it around, and then your splice comes in, and then we loop it around. Out here, we tie this down with wire ties. So it's a pretty good sized splicing tray. This was actually inside a splicing tube that Bell South uses. And it's a big old underground thing, and all these splicing trays were down inside that. And there must have been 10 splicing trays. So this would be what we would actually put our splices in. And it has a cover, it has a plastic cover that goes over the top of this. Are we okay? That makes sense? So what's that splicing tray for? Well, it's in there to protect those splices. because what did we do when we spliced it? We stripped off all that protection. This is what we have on there. This is splice protection. So we actually have one of these over in Building A. And then the splicing tray was inside this, and they were put in there in layers. And I think there was, I don't remember how many of them there were in there. And this was donated to us by ATT or Bell South. These are different type of connectors. Can y'all see these? These are crummy pictures. We have what we call an ST connector. Some people call this a Sierra Tango. And then we have an SC connector. So the connector on the cable that we passed around was an ST connector. This guy here is probably the most predominant connector used in the field, followed by the SC connector. SC connector is very popular because it is a quick disconnect. An FC connector, an SMA connector, and we have most of these. An FDDI, we have a cable that has this on there. We don't have a mini B and C. We did have a Biconic connector, but I can't find it. And so we don't have this one. RJ connector. An ST feed-through, we do have these. We can use these to temporarily splice a cable together if they've got connectors on it. We have an SC feed-through. Let's see if they have one of those in here. Yeah. Let's see what we have in here. This is an FC style feed-through. This is an ST feed-through right here. So I'm gonna, in fact, instead of passing this around, I'm gonna show it to you because y'all can mess this up. Now y'all are gonna be able to handle it. So this is a feed-through. And this is for an ST. Of course, it's got protections on it. Keep you from getting out of there. So let me put this here. And you'll see how it works. Not much to it, right? We call this a bayonet type connector. So what we would do on a cable is this is the way a bayonet connector works. For one thing, this is an ST connector. It's got a little key on it, so it's a key connector. Okay, can y'all see the key? Got a little low tab that's sticking up right here. And then if you look at the female, it's got a slot right here. So the first thing we have to do is we have to line up the tab and we slide it in. And this thing here is the actual bayonet itself is spring loaded. So what we have to do is we have to push it down and lock it in. These are the same the connectors we use for our oscilloscope, and these guys right here, these are also bayonet connectors. So what it is, it's got a spring in it that does what? It pulls it in, and then it latches down. So what I could do with this is I could come here and do this, right? So what we can do is we can connect two cables together that have already been terminated. Now this is not the way we would splice it. So you can see the different parts of the connector that are used to not only align and actually protect the actual fiber itself. Here goes Swiss. What did I do about their end cap? Oh, there it is. So what you're seeing there is what we call an ST feed-through. We have an SC feed-through. I think there's one inside here too. And then we have an adapter. There's the cap. I don't see an SC see-through. This is going to adapt it over for the different cables. So these are nice pictures of each. SMI, FDDI, which is Fiber Distributed Data Interface. This guy here has an ST connector on it. I'm sorry, SC. This is an FDDI connector. We got these. This is actually an FDDI interface card right here that went inside a switch. So you can see how that plugs in there. Oh, this is an FCPC connector right here, our terminal. We don't have a DIN, so we have a SC connector. That's what we passed around here. We have a ST connector. SCON connector is very, very similar to FDDI. We have an FDDI connector. What else do I have? I don't see anything else, guys. I think I brought out all the cables I have back over here. So the FCPC cable, this is used predominantly for single mode fiber, and in multi-mode fiber, the ST and the SC are the most popular. So y'all, I passed one of these cable connectors around. Now the trick is to put these cables, put these connectors on there, right? How do we do that? And that's one of the labs that we're going to look at. Okay, when we terminate these, and then we'll after this we'll start looking at the lab we're going to do, and we'll do it, like I said, we'll do this as a class, is there's three parts to a connector system. We have the connector plug, then we have the receptacle, and then we have the adapter that we're going to plug this into. Are you okay? Yes or no? Now, the connector itself, we have these parts right here we have to understand. If we don't understand this, we can't read the directions that tells us how to terminate these things or to put those splices on that. First of all, these are the parts, typical parts of a standard fiber connector. We have something we call the ferrule. We have something we call the retaining nut. We have something we call the back shell. And we have something we call the heat shrink boot, or this could also be heat shrink. Ours actually has a boot. And then we have something referred to as the cap. Now the cap is, and these are the parts right here. So the ferrule. Of course, I need to go in and get an actual connector. So the ferrule is actually what does the alignment of the fiber. So this is the ferrule right here. It can be plastic, it can be ceramic, or it could actually be metal. So on some of these I showed y'all, they were metal. Some of them are plastic or ceramic, and I've never seen a plastic one. Okay, everybody know what the ferrule is. So ferrule, we need to keep it really, really, really clean. It's got a little tiny hole that you can't even see on the end, which is where the fiber is going to come out. And this is sized for 125 micron cladding. Then we have what we call the retaining nut. This is the guy right here that actually retains it inside the other connector or inside the adapter. And then we have what we call the back shell. The back shell is where you're going to crimp to the Kevlar and the outside jacket. We okay? Then we have what we call the what? Go back to my slide. Ferrule, retaining nut, back shell. Okay, well, okay. And then we have the boot. So on these are cute little boots. These are boots. These are boots. And here are the actual, I might run over my wheelchair. This is the actual back shell. Got a little off. Broke. I'll take the back shell off or not. Oops, there with my connector. The back shell is where we actually crimp. Can y'all see that? Of course, what we want to do is we want to crimp this onto the Kevlar, right? And also the inside jacket. We'll look at that in a minute. And then we have the end cap, which is this guy right here, which we always leave on these things if we're carrying them around or don't have them installed into something. But you need to take that cap off when you do when you put it inside where it's going to go. So anytime we pull that thing off, we need to put that end cap on there instantly, because if you don't, it's going to get garbage and debris on the outside of there. And basically, we could go through all these different types of fibers, and we'll see all they basically look the same. It's the same parts. Okay, so this is a good place to stop. And then we'll come in and we'll look at the lab we're going to do. So we'll do this as a class, and then I'll let y'all fall back into y'all's individual labs.